Depth-first search. Consider the following algorithmic problems in graphs. Is a given graph connected? Is a given graph bipartite? Given a graph and two of its vertices, find a path joining these two vertices. Problems like these, and many others, can be solved by simply traversing the graph. Graph traversal, also known as graph search, means visiting every vertex exactly once in a well-defined order. There are many ways to traverse a graph. Each traversal strategy is characterized by the order in which the vertices are visited. Breadth-first search and depth-first search are the most commonly used approaches. In this video, you will learn about the depth-first search algorithm. Depth-first search, DFS. DFS is a graph traversal algorithm that starts from a selected node, called the source or starting node, and goes deeper, as far as possible, by visiting new nodes. If it is impossible to proceed, backtrack one step and continue visiting new nodes. In other words, the idea behind DFS is to go as deep into the graph as possible, and backtrack once you are at a vertex without any unvisited adjacent vertex. During a traversal, it is essential to track which vertices have been visited, because the graph can contain cycles, which may bring you to the same node again while traversing it. To avoid processing the same node again, use a Boolean array that marks the node after it is processed. While traversing the graph, one can mark the edges that reach a new unvisited vertex. These edges are colored in red. The graph induced by these edges is a spanning tree of the given graph, and it is called DFS tree. The data structure that precisely describes the step-by-step walkthrough of the depth-first search is a stack. A more precise description of the DFS algorithm is the following. First, initialize a stack with any starting vertex, and mark it as visited. All the other vertices are initialized as unvisited. Second, while stack is not empty, do let V be the vertex on the top of the stack. If there is an unvisited vertex W adjacent to V, then mark W as visited, and push it to the stack. Else, remove V from the stack. To illustrate the algorithm, let us apply it to the previous example. Let us initialize a stack with the starting vertex A, and mark it as visited. Then, the stack is not empty. Take the vertex on the top of the stack, which is the vertex A. If there is an unvisited vertex adjacent to A, we mark it as visited, and push it to the stack. Let us suppose that we mark vertex D as visited, and push it to the stack. Again, we take the next vertex from the stack, vertex D. If there is an unvisited vertex adjacent to D, we mark it as visited, and push it to the stack. So, we mark vertex E as visited, and push it to the stack. Continuing the algorithm, we take the next vertex from the stack, vertex E. If there is an unvisited vertex adjacent to E, we mark it as visited, and push it to the stack. So, we mark the vertex H as visited, and push it to the stack. Continuing, we take the next vertex from the stack, vertex H. If there is an unvisited vertex adjacent to H, we mark it as visited, and push it to the stack. Every vertex adjacent to H has been visited. Thus, we remove H from the stack. Take the next vertex from the stack, vertex E. If there is an unvisited vertex adjacent to E, we mark it as visited, and push it to the stack. So, we mark vertex B as visited, and push it to the stack. Following the algorithm, the next iteration marks vertex C as visited and push it to the stack. The next iteration takes vertex C from the stack. Since every vertex adjacent to C has been visited, we remove C from the stack. Vertices B and E are also removed from the stack for the same reason. The next iteration takes vertex D from the stack. Let us follow the final iterations of the algorithm.